Okay, so let's start. So where did we leave off? We talked about decision trees. We basically understand the decision tree learning algorithm. And you are playing with it now in your homework. I'm going to get a little bit later to talk a little bit about that. So I just want to remind you what we did last time. So we talked about ID3-based algorithm for decision tree. I went specifically to this slide because when I went over this slide last time, somehow I thought that there was a mistake here, but there wasn't. So just to remind you, we already chose Outlook to be the root node. And then we split the data into 3 subsets. Those examples for which Outlook is sunny, there are 5 of these. Those for which Outlook is overcast, 4 of these. Those for which Outlook is rain, 5 of these. And here we looked specifically at those examples that are on the left node from your perspective, these 5 examples. And we had to choose among these 3 which is the next node to choose. And I put here the entropy calculation. It was correct. It's actually easy to see that if you look at humidity, for example, you have 3 out of the 5 that are high, but they're all no, so the entropy is 0. 2 out of the 5 are normal, but they are all yes, so the entropy is 0. So we just stay with the 0.97. Similarly here, if you look at temperature, you have 3 values. But if you're looking at hot, it's all no, so it's the entropy is 0. If you're looking at cool, it's all yes, so the entropy is 0. If you're looking at mild, it's split between no and yes. And so in 2/5 of the cases, the entropy is 1, because it's uniform. And the same thing you can do for wind, basically just reminding you what we've done. Okay, so the example is correct. So that's what we did last time. We played a little bit more with this and finished talking about decision trees. The next thing, and we're going to go back to it a little bit, but I just want to remind you that at the end of last time, we talked about overfitting. And specifically, I wanted to give you some intuition. Where do I want to stop here? For why overfitting is important. You're going to see it again in your homework. And give you a kind of a beginning of a way to think about why is it happening, and how can we understand how well the model that we learn is going to do in the future. And we developed these 2 notions, all of them with the goal of understanding why is the expected error behaving this way. That is, why is it going down at the beginning as a function of model complexity? Think about the size of your decision tree. As you grow your decision tree, the hope is that your error goes down. Error on what? Error on some test data, set aside test data. But what happens is that while indeed it does go down at the beginning, it's going to go down, it's going to go up at some point. And this is where we said that overfitting occurs. So we explained it using these two notions. I'm not going to go into the details now, but I want to focus on one important point that we'll see multiple times this semester. One of them is the variance. That is, how susceptible is the learner to minor changes in the training data. And the intuition that I try to sell you on is that as the model complexity grows, you're more susceptible to changes in the training data. You have a lot of flexibility, and therefore you take every example seriously because you can, and you're going to change your model. The extreme case would be that you have in your hypothesis space only one function. You don't care about the data. Change the data, you're still going to return this function. If you have a lot of options, every example will cause a change. So that's one. And the second one is what we call bias, which you can think about how far am I on my test data from the true performance. And you would expect that this will go down as the model complexity goes up. And again, those of you that already played with your decision tree in homework 1 understand this, because if you have a very, very expressive function, that is model complexity is high, you can feed the data. So the bias is going to be low on your training data. The truth is that is a mix of these two. So as the model complexity goes up, the bias goes down, but the variance goes up, and therefore you want to catch your model somewhere in the middle. So this bias, this balance between simple models and complex model is something that is going to stay with us for the rest of the semester. And on the left side here, we have simple models. We underfeed the data. On your right side, we have complex models. We overfeed the data, and we want to be somewhere in the middle. So another way to think about it is a trade-off between the empirical error. What you see on the training data is going to go down as your model becomes more expressive, because it can. But on the other hand, in the future, you may suffer from that. Okay, so yes?
So is there any difference between bias and empirical error?
It's another way of saying the same thing, yeah. So mathematically, it's defined a little bit differently, but that's the basic idea. So empirical error is going to go down maybe to 0 if you have a very, very expressive model, but you may not want to be there. Okay. And then that led us to thinking about overfitting. This was a detour from talking about decision trees. And in the context of decision trees, we talked about pre-pruning and post-pruning as ways to avoid overfitting. Basic idea, I don't want to keep the whole tree. I want to shrink the tree a little bit. I know that I'm going to suffer a little bit in empirical error, but hopefully I'm going to generalize better. And we also talked about a little bit how can this be avoided with linear classifiers. Again, just giving you an idea to think about, because we're going to talk about it later. In fact, maybe at the end of today, we're going to start going back to linear classifiers, definitely next time. And it's important to think about how these ideas are going to be dealt with in that context. Questions so far? Okay, so that's where we were last time. I want to go back to trees now that we have a basic algorithm, to talk about a few other bells and whistles that have to do with decision trees. Yes?
How do you choose between pre and post-pruning?
Flip a coin. Basically, in your package, there are going to be multiple options, and you're going to try them. There is really no theory here. Yeah. But here is another way of dealing with pruning. again, something that is an option in the packages. So we talked about the fact that decision trees can be represented as rules. I mentioned it when I talked about the expressive power of decision trees. We thought about it. We said that it could be a DNF. Specifically, if you take one path down from the root to a leaf, you can think about it as a rule, right? So you have, in this case, outlook equals sunny and humidity equal normal is yes. That's a rule. Another rule, outlook equal rain and wind is strong, then no. So you can take your decision tree and rewrite everything as a set of rules. Advantage, comprehensibility, for example. Some people want to see a set of rules because it's easy to read, it's clear what's happening, or clearer what's happening. Now, one interesting thing is that if you want to do pruning for your decision tree, you can also do it at the rule level. So, first of all, I'm taking the decision tree that I got, then I'm rewriting it as a set of rules, and now I'm going to do pruning. What does pruning a rule mean? So a rule is a conjunction. It's this condition, and this condition, and this condition, then yes. What does it mean to prune it? Yeah? I want to make it more general, so I'm going to remove one of the conjuncts, and I'll remain with a rule, but a rule that fires more often, right? A more general rule. So it's kind of like going up the tree, but it's not exactly like going up the tree. Why is it different than going up the tree? And the reason I'm asking is because I want you to think about trees and make sure that we understand what's happening here. So what's the difference between pruning the tree and pruning one of the rules that was generated from the tree? Yeah?
I think pruning a tree is like going up to like a upper level, while pruning the condition is like cutting off some of the branches or leaves.
Right. So when we talked about pruning, we actually said, let's go bottom up. Look at one of the leaves, eliminate it, and fold everything up. When you do it at the rule level, the rightmost conjunct, but of course conjunctions are not ordered, but the way I've written it here, the rightmost conjunct corresponds to a leaf, to the last condition. But in principle, I could eliminate another conjunct from the rule, and therefore it's kind of like disconnecting the tree a little bit. So it's not the same thing. And again, if you have some statistical measure according to which you're going to prune, you may end up doing that, and it's important to realize it's different. Okay, so what else do we want to say about decision trees? So a couple of things, some of them are more important than others. All of them serve to get you to think about the generality of this. And there's a lot more bells and whistles with decision trees. There's been work on them for 30 years, and I'm just giving a few of the important and practical details. Yes?
Like when we were doing the pruning by rules, would that be equivalent to eliminating the example that you had in the tree? Would that be equivalent of getting rid of outlook altogether? Or would that be equivalent of sunny, or you could choose whatever it is?
You could eliminate, in principle, outlook equals sunny from the rule. That's it.
Or could I take the whole outlook, like a of the variable, and just use humidity?
So if you're pruning at the rule level, at least pruning a single rule will not get rid of all of outlook, because outlook appears in 3 rules. But maybe at the end, you'll end up getting rid of outlook. So that depends on the data that you have and your statistical tests for how to decide when to eliminate. Unlikely that this will happen because outlook was chosen for a reason to be the root of the tree, but conceptually could happen. Okay, so one interesting issue, we always talked about discrete conditions in the trees, but it could be that some of your features or all your features are actually real valued, right? So it could be height, width, temperature, and you want to be able to deal with it. Again, the conditions in the decision trees are discrete conditions, the nodes, but you can discretize. So one simple way to discretize is discretize ahead of time. So if you have something like a height, you can discretize into big, medium, small ahead of time. And now when you see numbers, you place them into one of these buckets, and you run the algorithm as is. A more interesting way to deal with it is basically to do it in a data-dependent way. So you have an attribute A, and you want to form conditions of the form A less than C for some C, or for multiple Cs. And you're going to do it in a way that depends on the data that you have. So you first look at the data, and then you decide what values, what buckets do I split A to. So for example, if you have a feature A, I'm going to sort the examples according to the values of A. And for each ordered pair of values, x, y, that has different labels, I'm going to place a constant, and I'm going to split it in the middle. This will give me all the interesting splitting points. I may not choose to use them in my algorithm, but at least I'm going to have them as my attributes and allow my decision algorithm to deal with it. Example, I have length here, and these are my values, 10, 15, 21, 28, and so on. And corresponding to them, you will see the class labels. So my suggestion here is to choose threshold that correspond to changes of the labels. Otherwise, it's not going to be interesting to do. So in this case, 12.5, between 10 and 15, there is a change of label, so I split it right in the middle. Between 28 and 21 and 28, there is a change of label. I'm going to split it in the middle. Now, of course, why do I split it in the middle? No good reason, just because I don't have a reason to do it otherwise. But if you do have a reason, you can split it otherwise. But the key idea is that in a data-dependent way, I invented new attributes. And now I can run the learning algorithm as is. OK. A second important extension is the one that we deal with missing values. Someone asked a question about it last time. Yes?
Going back to the previous slide.
Yeah.
Wouldn't it always be possible to place a threshold, say, all the way to the left, always leaving one data value to one side and all the other data values to the other side, and that way you can ensure that your entropy is zero, even though you don't really get that much information out of it?
Relative to this specific attribute. Yes, yeah, of course, you can do this. So basically, you'll say all my example have L greater than 0 here, or all my example have L less than 100. Yeah, so basically, it's equivalent to throwing away L, right, for my representation.
How would you prevent something like that?
Well, it's your problem, right? So you have to try to do the best with this. If you decided to throw away one of the attributes and run your learning algorithm without it, you're not going to get results that are good, right? So all I'm saying here is you have data. Your job is to run the learning algorithm on this data so as to maximize the amount of information you get from this data. And this is a suggestion. If you want to do it in a way that says, you know what, I'm not going to deal with L, I have enough other features, let's throw L away, you can do it explicitly, or you can do it implicitly with your trick, but just...
what I'm saying is that wouldn't this approach of picking different thresholds always be biased towards a threshold that kind of is really easy to pick?
So I'm not sure where in the process you are.
So I'm saying...
Are you the learning algorithm now?
No, so this step of checking different thresholds.
Yeah.
I'm saying the 12.5 threshold will always have an entropy of 0, right?
L equal,
Because for
no, there'll be examples below it, and there'll be examples above it. Why would that be 0?
but if you pick it so there's only one example below it, then you automatically know what that example is. So you don't really get that much information out of it.
No, but you're talking about training data here. First of all, there could be many examples. I mean, all I showed is, there are examples with values 10 that are negative. I don't know how many. I'm not sure I'm getting the question then. So basically, it's a feature extraction step. So let's go one step back. So when we started talking about decision trees, I cheated a little bit. I told you, you know what? Unlike SGDs or other linear classifiers that we're going to see in the future, here is data. You have to do some feature extraction. And then you're going to maybe add expressivity to the features one way or another. And then you're going to run your training algorithm. In decision trees, the feature extraction step is minimal. Basically, it's expressive. It can do all the work for you. What I'm showing you here is sometimes it's not completely correct. Sometimes you actually have to look at your data and decide how to extract features, because if you don't do this right, you will not be able to exhaust the information that L gives you here. And I agree with you that bad choices here will be bad in the sense that you will not get information from L. Better choices will give you information from L. Yeah?
How come we don't have a separate threshold between 20 and 32? Because we're shooting from a negative example to a positive.
Oh, no, I didn't say that this is exhaustive. These are just examples, yeah. Okay, so missing values. So someone commented last time that sometimes when I measure attributes, for example, medical domain, I measure fever, blood pressure, other blood tests, and so on, some attributes could be more expensive than others, or some just people that gave me the data did not bother to take for one reason or another. And my decision tree algorithm may be facing with data that misses some values. And you can think about it in two scenarios. So you can be missing values in your training data or in your test data. So let's think first about training data. So what is my goal? I get this collection of examples, and I want to be able to evaluate the gain relative to a specific attribute where some of the examples are missing values for attribute A. Here is an example, back to where we were before. So I have this, I already chose Outlook. I'm looking at Outlook equals sunny, 5 examples. I need to choose the next node. But under humidity, example 8 is missing a value. And I still need to compute information gain for each one of the attributes and choose among them. So I can go with temperature. That's easy. And just because for temperature I have all the information, what should I do about humidity? How do I compute the information gain here? Suggestions? Yeah.
Just take the majority from the rest of the samples.
Majority of what?
Like, in this case, it looks like it's split, but if there was more, maybe go with the, like, in this case, I would pick either or.
Yeah,
But
so basically,
the majority, the one that was, the most.
suggestion 1, fill in the value. You see that I have some numbers for which humidity is high, some number of examples for which humidity is normal. Choose the majority and place it there. In this case, let's say I'm going to do high. Yes?
You can also just pretend like that data doesn't exist, and so
I can eliminate example 8 altogether. true, then I'll have to think about whether I eliminate example 8 also for other attributes or not. But that's certainly an option. So one option is majority. Other options? Yes?
You could look for when they're all sunny, but you could look for when the temperature was mild and say that it's normal because number 11 was normal when it was mild.
Okay, interesting option. What are you really doing here? So you're going beyond the standard algorithm for computing the information gain of humidity. You're looking at the rest of the data, and I'm looking for a verb. What are you doing? Inferring. You're learning from the rest of the data what could be a good way to complement this missing value. So let's skip this. I want to go back to it. Before that, I want to suggest another version of what you suggested, which is who said that the values have to be integers, right? So when I'm computing entropy, I could assign the most likely value. In your case, let's say I chose that it's going to be normal. So this is my first option here. Fill in, assign the most likely value of xi to s. So I did this argmax over all possible values, and I chose normal. You can see that it's actually a tie, but I still chose normal. But notice that when I compute entropy, I can actually deal with fractional counts, right? So I can say, you know what? I have 2.5 examples that are high and 2.5 examples that are normal, because I don't know how to choose between high and normal. So I'm choosing half from each. If I had 3 high and 1 normal, I would choose 3/4 high and 1/4 normal. In the calculation of entropy, you can put fractions. Okay? Do you see the difference between the first option and the second option? I'm a little bit more general. But the other suggestion, actually, I was waiting for something like this. So this is a very interesting suggestion, right? So the suggestion is, you know what, you have more data. And maybe you can use the rest of the data that you have as a way to predict the likely value of humidity, for example, 8. For example, you can look at the y even, right? You see that there are 3 no's and 2 yeses. Under the missing one, or for the example 8, which is missing a value, it's no. Maybe it's more likely than to be just like the high, because, for example, 1 and 2, it's also no. Or maybe I can look at another attribute. You suggested to look at temperature and correlation between the temperature column and the humidity column and try to fill in based on this. Either way, the idea is, let's try to learn. I'm using learn in quotes here because we didn't define exactly how we're going to learn, what is the representation we're learning into. But let's make an intelligent guess of what this missing value is, fill it in, and continue. That was your suggestion, right? And this is, in fact, is going to be an important step in an algorithm that we're going to learn later this semester. It's going to be called EM, for expectation maximization, where the idea is you have a missing value, you're going to guess it. Try to make an intelligent guess. Learn with this guess, make predictions, and then go back and see if you need to correct this guess, and keep on going this way. And we'll show that under some condition, this is actually the right thing to do. We're going to give it probabilistic interpretation. But even here, when there's no probability involved, you know, it's a kind of discriminative learning algorithm, we still can think about this interesting idea. Okay, so we have several options for training. We also have to do stuff like that in test, right? So you give me an example. You want to get the label of this example. You already have your decision tree, but you have a missing value. So Here's an example here. I learned my decision tree. I got an example, and the value for humidity is missing. What do I do? So I'm starting with Outlook. Outlook is sunny. I'm going down to your left, and then I don't know what to do because I don't have a value for humidity. Suggestions? Guests? Yeah?
Go with the worst case scenario, so go with whichever has the higher number.
Okay, so basically do some kind of majority prediction between normal and high, and go with one of them. In this case, it's a tie, so there's nothing I can do. What if I'm missing Outlook in this example? How would I predict? Yeah? You can change the order. Of course, we have a reason why we choose Outlook, but what can we do? It's missing. So that's certainly an option. Another option? Well, you could say something like, Outlook takes 3 values. It could be either sunny or overcast or rain. Let's assume that I have no way to prefer between sunny, overcast, or rain because they occur in the same probability. So I'm going to say, in a third of the cases, it would have been sunny, and then I would say yes. In a third of the cases, it would have been overcast, I would say yes. In a third of the cases, it would have been rain, I would have said no. So I'm voting yes. 2 out of 3. Now, of course, here I chose uniform distribution. If your data tells you don't choose uniform, you'll choose another distribution. But essentially, you're working by majority or by voting over what you perceive to be the distribution of the missing value. If you have good ways to estimate this distribution somehow, using the trick from the previous slide, you'll do a better job. Otherwise, you'll just resort to doing it uniformly the way I did it here. But basically, the idea I want to send here, this is actually an important problem that you're going to deal with in many, many realistic cases. We want to be able to develop methods. Okay, so just to finish this with a couple other ideas. So as I said, there's been a lot of work on decision trees. And I want to highlight a few things. So one is, again, a question that someone asked last time. It's quite possible that different attributes, different features have different costs. I want to be able to incorporate it into my information gain. So you could imagine ways to do it. I mean, people have already done it. Some of the packages have that. So this will be one important change. Another related thing is we talked about computing entropy. When you compute entropy in your problem set, you will see that, or you've already seen it, that entropy is sensitive to how many values the attribute takes, right? So if the attribute takes 2 values, the max entropy is going to be 1. If the attribute takes 8 values, the max entropy is going to be 3. And if you have in the same problem attributes that take very, very different number of values, you may want to think about, do I want to adapt my information gain definition so that it takes this into account? As I said, because the range of entropy varies with the number of values. So that's another thing people thought about. Oblique decision trees. So think about the type of decision trees we've learned so far. Let's take the case of continuous variables. We took this L, and we said L is greater than something, L is less than something. So we took basically the space, let's think about it as a plane, and we split it into axis parallel rectangles. Now, you could imagine that you want a more expressive way to split the space. Let's say that in each node, rather than saying L is greater than 5, I'm referring to these examples here, L less than 12.5, L less than 45. Maybe I want to take two attributes, L and A, and say, I want a node that says L plus A is greater than 5, or 2L plus 3A are greater than 5. So essentially, I'm going to have, rather than an axis parallel decision boundary, I'm going to have a more general decision boundary, really a linear function. So these cases are called oblique decision trees. They are more expressive, as you can see, as you can imagine. Of course, learning them is also going to be harder, because you first have to decide, what do I put in the nodes? And once you have nodes, you have to learn over the nodes. So this is the generalization of just thresholding the L that I showed before to something a little bit more complicated. Finally, incremental. So in many cases, we want to run incremental algorithms, right? So we already thought a little bit about it when we talked about gradient descent and stochastic gradient descent. The idea in gradient descent was, you give me all the data, and I'm learning a learning algorithm on all the data. Every change that I make, every gradient step that I make, I'm using the whole of the data. As opposed to it, in stochastic gradient descent, I do a step for every example. I don't need to see all the examples together. I don't need to keep all the examples together. I just go one by one, or if you want, mini batch by mini batch, 10 examples at a time. But I don't have to have sufficient memory to keep all the data even. What if I want to do this with decision trees? Right? So I have so much data that I cannot keep it in memory. I still want to learn a decision tree in a streaming fashion. So existing decision trees algorithm can be modified to deal with that. One issue to think about is consistency. Someone asked me a question at the end of last time. I can't remember. I can't see you. It's somewhere there. A good question about what happens if you get in your data two examples that are identical with a different label. What will you do? What will your decision tree algorithm do? Yeah.
Discard them.
If you see this, you can discard one of them or both of them. If you don't, what will your algorithm do? Yes?
Probably just create a tree based on the first instance.
You could, and then what will happen?
Whichever was the first, like positive or negative, it would choose that as the default.
Okay, but basically that means that your algorithm will not be, the model produced by your algorithm will not be consistent with the data anymore. Now think about running your decision tree algorithm. What would really happen to the decision tree algorithm if you include data with a contradiction? Okay, let's leave this as an open problem. Now you're playing with the decision tree algorithm in the homework, so think about it, introduce something like this to the algorithm and see what happens. In this specific case, when we talk about incremental, you have to think about it in a slightly different twist, which is, let's assume that all the data is when you started, the data was consistent. Now, suddenly, you start getting data that contradicts earlier data. What will happen? So all these issues can be dealt with in the context of incremental decision trees. Okay, so let me summarize. Do think about the problem of contradiction. So we talked about decision trees. We talked about the hypothesis space of decision trees. It's important to understand. Hopefully some of these lessons will become clearer as you play with your homework problem sets. we talked a little bit about issues of extensions and a little bit about evaluation. I'm going to move on now to talk about evaluation. But before that, I want to talk about one of the key issues that in modern machine learning is important from the perspective of decision trees, and that's the idea of decision trees as features. So what is commonly done now is rather than using decision trees to represent one single target function, it's becoming common to use small decision trees as features for other algorithms. The reason this is being done is because decision trees are an interesting and expressive class. They can learn simple functions that can be used as features. Again, remember what we've done a few lectures ago when we talked about blowing up the feature space, starting with the raw data that you have, generating more interesting features on top of it. I gave an example of conjunctions, and I gave an example of squaring X. Decision trees are doing just that, but in a more expressive way. They will take a few of the features and build a small decision tree that you can use as features. Hopefully, this will avoid some of the issues that big decision trees will carry, basically overfitting. So when you do this, you actually think about each of your small decision trees as an expert. It covers part of the area of X. It knows what to say about this specific X. It may not know what to say about other regions, but then when you combine them together, you know what to say about everything. And then on top of it, you learn another function, typically a linear function, over this feature. So one of the important algorithms that we're going to touch upon a little bit later in the semester that is being used this way is boosting. I'm going to give now an example for how this is working, kind of very hand-wavy example for now. Yeah, you can see it, I hope. So here is a toy example. So I have a collection of, I think, 10 examples here, 5 positive, 5 negatives. It seems a relatively complex hypothesis space, or instance space, right? So I don't know exactly how to separate the pluses and the minuses in this example. Can you see it well? The way I'm going to do it is I'm going to learn decision trees, very simple decision trees, in order to do it. So here is my round 1 decision tree. What did I do? I took the decision tree, I call it here H1. All the examples that are to the left of this line, X is less than this value, I'm going to call positive. So you see that I have 2 positive examples there on the left. The rest I'm going to say negative. That's my first decision tree. Now, you know I made a mistake. I made 3 mistakes. I circled here the mistakes that I've made. So that's decision tree 1. There are also some constants here that are on the right and a few other things. Let's disregard these now. We're going to attend to them in a few weeks. At this point, I just want to run through this example. So now, round 2, I had my first decision tree. Now I'm ending another decision tree. The second decision tree here, the second box says everything that is to the right of this vertical line is negative. So I have these 2 negatives. The rest I'm claiming are positive. Again, I made mistakes. I circled these mistakes. And I'm going to keep on going. So this was my first decision tree. This is my second decision tree. Now I have my third decision tree. And I'm saying it's on the y-axis here. I'm saying everything that is above this H3 line is positive. And again, I made mistakes. Not everything is negative. These 2 are exceptions. Not everything is positive. This is an exception. 3 mistakes out of the 10 examples. This is my decision tree. So far I learned 3 very simple decision trees. They're called decision stump, but they're even simpler than the decision stump that you have in your homework. It's a 1 decision rule. And then, for my final hypothesis, I take a linear function over this. So I took 0.42 over the first decision tree plus 0.65 over the second decision tree plus 0.92 over the third decision tree, and it splits the space this way, and it's perfect. All the pluses are pluses, all the minuses are minuses. No mistake. So what did I do? I learned 3 very simple decision trees. Each one of them made mistakes. And then I learned a linear function on top of these decision trees, basically assigning weight to each one of the decision trees. And I got perfect classification. Yes?
Maybe just an example, but this seems like it'd be really susceptible to overfitting data.
Why?
I feel,
So the suggestion is that this could overfit the data significantly. What's your intuition driven by?
I mean, use an example then.
Okay, so of course this is a toy example. The title was toy example, and it is a toy example. But okay, so whether you're right or wrong will depend on largely 2 things. First, how do I choose my decision trees? 2, how do I combine my decision trees? And I didn't say anything about it. Now, in your homework, you are doing something like this. You're choosing decision trees. How do you choose the decision trees? What we ask you is, you have a bunch of examples. Choose a random sample of those, learn a tree. Choose another random sample, learn a tree. Do this 200 times, I think. And now you have trees. These trees are to be used as features. What does it mean it's a feature? A feature is something that takes an example and returns a value. I'm on in this example, or I'm off in this example. So you're going to do this for each one of the examples, and essentially you're going to convert your feature space that was 390 features to a new feature space, which is the values of my 200 decision trees on each one of the examples. So now each example is going to become 200-dimensional example, the values of the decision trees, and then you're going to send it to the learning algorithm. What I did here is somewhat similar. I had examples. The examples were 2-dimensional. I converted the 2-dimensional space to a 3-dimensional space. For each example, I had the values of the decision tree. And now I learned the linear classifier over these 3 dimensions. 0.42, 0.65, 0.92 were the weights of my linear classifier. It's not exactly the same because here I learned the decision trees kind of one by one. You learn them conceptually together. And here I didn't tell you how I assigned the values. In the homework, you're going to use SGD to assign these weights. But conceptually, very similar. And if we know how to do this right, in fact, this is going to be a very, very good algorithm. That for many years in the literature, people actually thought that it never overfits, which is kind of curious. We're going to talk about it when we'll get to boosting. Questions on this? So I wanted to relate this to your homework because I know that this part of the homework sometimes is conceptually difficult. Everyone is clear about what does it mean to take your data and convert it from this 390-dimensional space to the new space, where each dimension is really an output of a decision tree that you've learned before. Questions? Who's tried it already? Very few. Okay, that's why there are no questions. If you haven't tried, please do. As I said last time, I'm not advising you to start the day before it's due. Do it earlier. So hopefully this will shed some light on what we expect you to do. Okay, so let's move on. Okay, final questions on this before we move. So the last few minutes here, I want to spend on experimental machine learning. So really, it's an experimental field. We have to know how to do experiments. You have to know how to do experiments, and we're going to give you some experience with this through the problem sets. The first thing that I want to suggest is be organized. In this and in future homework, you're going to run a lot of experiments, probably more later. Don't expect to basically sit next to your laptop and do everything there. Be organized in the sense that, write scripts, run them, record results, come back tomorrow morning and look at what you got. Basically, it's going to be essential for you to do this. And in some cases, the reason we ask you to do a lot of experiments is to force you to do it the right way. Okay, so some of the basics. We always think about training data and test data. Quite often we think about it, somewhere between 70 and 90% is going to be training. Somewhere between 10 and 20 is going to be test. The reason, of course, most of the data we want to train on, because it's going to give us better models, we need to have enough in test so that we can make some conclusions when we look at the results. If we don't have enough test data, it's not going to be significant. And we often need some development data. So we take our training data, we set it aside. We don't use it for training, but we use it as a way to tune parameters if our algorithm requires some parameters. So in the case of SGD, this is often the case, and you can use this. And you will see it in later homework also. So eventually, of course, you're going to train, you're going to look at your performance on test data. This is what we care about. Okay, so I want to talk about three things. One is metrics, second is methodologies, and the third is statistical significance. Can we believe what we see? So as I said, we have training data, test data, and often we have development data. In the homework, I ask you also to look at the results on the training data. Why did we do that? Who cares about how well the algorithm does on training? Yes? Right, so this is excellent. This is really a key issue. So I've seen a lot of more advanced machine learning practitioners that don't know how the algorithm does on training. They just show me results on test. And it's really important to know how well your algorithm does on the training data, even though you never report it. But in order to understand where you are in your development process, you have to understand this. And specifically in this homework, when you look at it, you learn stuff. You will understand where you are. You'll understand what is the difference between the different classes of learners that you're using. And it will be very informative. And this is basically a suggestion that I'm making for you now. Not only in homework one, do it later on. I think it's quite informative to do this. Okay, so how do we measure performance? We often think, and so far we didn't do it explicitly, but whenever we talked about classification, we talked about accuracy. Right? So measure how many examples you got right, how many examples you got wrong. In realistic problems, this is often not enough. And in many problems, you will have to measure performance differently. So this is accuracy, number of correct prediction divided by number of test instances, which is, and this is just 1 minus the error. But often we want to do other things. And often for a reason, because for these tasks, the specific task that you care about, accuracy is not informative. In fact, sometimes accuracy is not informative even when you deal with binary classifications. Examples? So the problem we gave you in homework 1 is binary classification. And we actually ask you to report accuracy. But can you imagine cases where accuracy will not be the right thing to ask? Yes?
Sometimes there are cases like testing someone where there's a big difference between the false positive and true negative. So you can have a really high accuracy rate, but it's very rare disease. You might have like a really high false positive.
Right, excellent example. So a very imbalanced data set, right? Where most of the examples are negative and just a few are positive. So the medical domain is one, but you can imagine, I'm sure, many other examples. Any other example for a very imbalanced data set? Dream up a case where you want to do classification. Yes?
Like, for example, if you want to know whether in a reef there's bleaching or not, the majority of population will be non-bleach, and you could just guess nothing's bleach and you could have a high accuracy.
Exactly. So in all these examples, you can just say no, and your accuracy is going to be very high, but it means nothing, right? You didn't really learn anything. So we want to be able to develop task-specific metrics. By the way, multi-class classification is another typical case of this. When you have more than 2 labels, accuracy is often not good enough. Again, for the reason that in almost all cases, it's not going to be uniform over the labels. So we want to develop another metric, and different tasks have their own metrics in applications. But one important example that is used often in many applications is that of recall and precision. So I'm going to talk about it here and define what I mean by recall and precision. We're going to use this picture that I kind of modified from Wikipedia, actually, because often these are being used in the context of information retrieval, but I'd like to use it here in the context of classification. So what you see here is the space of all the examples on the right. The right part of this rectangle are the negative examples. The left part of it are the positive examples. In the circle are those examples that you chose, your model chose to be positive. Okay? So, which means that the left part of the circle are those positive that are true positive, and the right part of the circle are examples that your model thought were positive, but actually they are part of the negative examples, so we call them false positives. Okay? And again, in this specific case, it's relatively balanced, but we want to, you could have done accuracy also, but we want to be able to think about recall, other metrics for this, which we're going to call recall and precision. So recall is going to be the number of true positives. I like to think about it as the number of positive identified divided by all the positives. So essentially, you're taking the left side of this rectangle in the denominator, and in the numerator you put the green circle, the green half of the circle, those that you actually identified. So you're basically asking, out of all the positives, how many did my model get? That's the recall. Okay? And then in precision, you actually have the same numerator, but you divide it by the number of predicted positives. Basically, you want to know how precise is my algorithm. From all those that I predicted positive, how many are really positive. Okay, so again, in the numerator, now you will have all those that you predicted positive, which is the whole circle, green and red part of the circle, and you take the left part of the circle as your numerator. This is, as I said, it's a very generic type of way to evaluate, and it's useful in many, many applications. Let's take a simple example. Basically, the examples that you guys gave me before. If I have 100 examples, but only 5% of them are positive, I can just say no, get accuracy 95%, but it's meaningless, right? My recall and precisions are going to be 0. I don't know a thing. On the other hand, let's take the example where, let's say I predicted 4 positive examples. You already see that my model is relatively good because the number of positive it predicts is not too far for the number of positives in the data. But 2 of the positives that I predicted are really positive, and 2 of them are actually negative. My recall is going to be 2 out of 5. Let's look at the picture again. Oh, yeah, I have it. My recall is going to be 2 out of 5 because the number of positives is 5, and 2 of them I identified. My precision is going to be 2 out of 4 because out of 4 positives, I identified 2 out of those that I claimed are positive. I claimed 4 are positive, 2 of them I did it correctly. So I'm going to get 2 of 4, not good results, but basically a better way to characterize how my algorithm is doing. Okay, so another way to think about all these things is a confusion matrix. Think about true positives, false positives, true negative, false negative. For each algorithm, you can think about it here, and you can go back to this picture and think about false negative, true negatives, true positive, and false negative, which I identified in this figure. And you can define, again, recall and precision and accuracy as a function of this. Again, recall is probability. You don't necessarily have to think about it as probability, but it's the ratio of those examples that is randomly selected positive is actually identified, that my model got it correctly. And precision is out of those that I claimed are positive, how many I got correctly. Okay, so quite often what we do is we don't think about it just as recall and precision, but rather as functions of recall and precision. We want to combine them, for example, to one metric, or we want to look at the relation between them. So we may look at a recall precision curve. As the recall goes up, the precision will go down, and vice versa. And we may even sometimes look at the area below this curve, kind of the integral of this, or some versions of these curves. Or we'll try to combine these two together. And one common way to combine these together is called the F measure. And I'm defining if the F measure. It's basically a harmonic mean of precision of recall, and it's balanced by this beta here. If you take beta to be 1, so this is going to be called F1, which is the most commonly used thing, what you'll get here is 2 times precision times recall divided by precision plus recall. This is a very commonly used metric. Now, you don't have to do F1. You can do F.5 if you want to emphasize precision over recall, or recall over precision, or F2 if you want to do the other direction. But basically, it's a way to get one concise measure from all these, from recall and precision. Questions? So I'm introducing it here. In one of the other problem sets, you will actually play with recall precision too. But as I said, if you do other tasks, if you do, I don't know, machine translation, you will have to invent or look at the literature for other metrics that people are using. Metrics really are task-specific often. Okay, so the next step I want to get to, and I see that I will not get to it today, is we want to be able to compare classifiers or models. Say that we have two classifiers. In your case of the problem set, you have decision tree of size 8, or depth 8, and depth 4. And you want to be able to choose which one you're going to use in the future, which is the best model. Or if you want, which is the best algorithm. Hopefully, this is a rhetoric question and you know the answer to this. Can we use the training accuracy to choose between them? Yes, no? No, why not? But what lessons could you get from the training accuracy that you don't want to get? How can you be misled by your accuracy on training? Overfitting. So it could be that one of them is going to do very, very well on training. It's meaningless. How would you get one of your algorithms to do very well on training? Lots of features is one example. Basically, another option other than lots of features, yes? You can hard code the input, okay, so that's an even more blatant way of doing it. But outside this, I like the idea of more features. Give me one other option. Yes? Very deep decision tree. So these two are two phases of increasing the expressivity of the model, and you can get down with your accuracy on the training data probably as low as you want, meaningless. So that we are okay with. What about accuracy on test data? Yes? Okay, so could be recall or precision. So everything I'm going to say in this part actually applies to a metric. Not necessarily accuracy, could apply to recall, could apply to precision. It's going to apply to statistics that I'm measuring. But is it okay to look at the numbers that I get on my test data and say, okay, so C1 is better than C2? Yes?
If we don't know if the distributions are similar or if the distributions of the test data now.
Okay, so first of all, is it even the same test data? That's important. But even when it is the test data, just one number often isn't sufficient for us to know whether we can, whether this algorithm is better than that algorithm. So one of the things that we want to think about is what are the methodologies and statistical tools that will allow us to actually determine with some confidence that one algorithm is better than the other. And just a single number, give me the number on test, isn't good enough. Because maybe the test data is very small. And therefore, if you get 80% on one and 82% on the other, it's a coincidence. Take another data set or test set, and you will get different results. So we want to be able to do this. And what you're going to do in your homework is you're going to do cross-validation. Cross-validation is a very standard way of doing it. Essentially, we're splitting training and test n-fold, we call, in this case. Typically, 5-fold is considered a stable test. So 20% of your data is going to be test, but you're going to sample 5 times the test data. In the homework, we actually gave this to you. So the picture you're going to see is something like this. Every time, 1/5 of the data is going to be the test. 4/5 of the data is going to be your training data. You're going to train and test and average these results. This is going to be a more stable way to compare classifiers. Even that, there is a question of to what extent we can believe it. And in order to more accurately address this, we're going to appeal to a theory of hypothesis testing, something that some of you might have seen in your statistics classes, and basically try to determine whether the difference that we see between algorithms is actually statistically significant or not. And there could be multiple tests for doing it, and the test that we choose might depend on what can we really get. So there could be multiple cases, multiple scenarios. And one scenario is the scenario that you are in your homework. You have all the data, you have all your models, you can compare results not only between the final results of the algorithm, you can actually look at each one of the test examples and see how each one of your models does on it, right? Now, if you go to the literature and you see someone published a model and they say, we are doing 85% on this data, and you have another algorithm that does 89%, are you doing better or worse? Typically, they will give you the numbers. They will not necessarily give you the prediction of their models on each one of the examples. So some of the tools that you could use in your homework, you cannot use when you compare to the literature. So next time I'm going to spend a few more minutes introducing hypothesis testing in the context of machine learning, and then we're going to move to the next topic. Questions? Yes?
In the end-over cross-validation, it appears as if you use a different set of training data and a different set of validation data for each algorithm that you're testing. What if in the training, what if there's some asymmetries in the data such that one algorithm has an advantage over another?
So that's why you do fivefold, which means in all cases, you're averaging over these 5 cases. So 2, it could be that one algorithm is very good on this 20% test data, and another is very good on others. So hopefully this will average out. Plus, so there are 2 issues. One, it will average out. Plus, there's going to be some statistical significant tests that will, in principle, account to the fact that there are anomalies in the data, and you can't always believe the number itself. So there has to be some error bar around it. So we're going to discuss it in more details next time. Okay, see you Wednesday. Hi.
So the recitation, you have 2 recitations, one on Wednesday, one on Thursday.
Yes.
And I only made it to Thursday, and I moved it to a time that I can't make it. So.
Oh wow! So now you cannot make any of them.
I have class from 2 to 4:30, and they moved it exactly where Wednesday is.
The reason we moved the Thursday one was that it turns that none of the TAs can make it.
So the thing is, I have class every
so you have
day
class
from,
when?
3 to 4:30, and every time it's. I mean, I can make like 30 minutes if I push it.
Yeah. Okay, so we will ask again.
If they can make it so that it's not like the same, because Wednesday and Thursday it seems to have like the same time.
I know, we started with a different time,
yeah.
And then it turns out that we cannot make it.
Like on Thursdays, I can make it anytime before 3. On Wednesday, also can make it after this class.
So maybe if we'll make it earlier on Thursday.
Yeah,
okay. Let me suggest this in the meeting tomorrow. We'll see what we can do.
I was making it, and suddenly they just sent it.
Yeah, I'm sorry about it. It's very difficult to we have 10 TAs and we have 150 students.
Yeah, no,
it's so difficult to make all the constraints. Yeah.
All right, thanks.
We'll try.
Yeah.
Hi. We haven't decided yet. Why?
Because I work, and it's hard for me to get home, so I watch
I see.
videos.
Yeah, you know, one reason I want to do it in class is because I want the people to be more awake. But I see the issue. I mean, I know that if I'm getting 80% of the students, I'm lucky. We'll see. But either way, we're going to announce.
Oh, okay, so it won't be
Yeah, yeah. It will not be surprised. We'll tell people. Yeah.
Thank you.
Sure.
Yeah, wanted to make a quick fix in the code. How's it going? Oh, nice. Congrats, I haven't even started it yet. Oh, what is this? Oh. My God. Thank you. I appreciate it. That's so nice. Nice. And thank you for the thing about that. Stupid clock. It's so obvious. Yeah, I'm trying to save it. No, I'm done. Just one thing is I wasn't doing the derivatives right. So now you said that U doesn't get a straight line? Yeah. I was wondering about that. So what I asked because when you do when you check the values of your, oh yeah, the values of like, oh yeah.
All right. There we are. I put that.